Hi, welcome to Intermediate Algebra, section 6.2, simplified form for radicals. So we're going to be looking at different roots here, square roots, cube roots, maybe some bigger roots, and we're going to be looking at how we can clean them up and make them as nice as we can. Kind of like we do with fractions when we take the numbers and we divide them down to reduce them as much as we can. We're going to do something kind of sort of, okay, maybe not really, but a little bit similar with radicals. So I'm going to take this in parts. There are really three things we have to be able to do. So I've got the first two on the board here, and then we'll see the last one here in a little bit. But let's get started. The first one is really quite simple. No fractions on the inside. Period. End of question. End of discussion. So to do that, we're just going to split the radical. Okay, you can see I wrote that down. We're going to split. And that works because we have a property for radicals that says if you have a fraction inside, you can split it. Where does that come from? I'm going to refer you back to exponents because when we had fractions with an exponent on it, you can take the exponent to both parts of the fraction. And since radicals are really kind of like exponents, we can do the same thing here. So we can split the radical across a fraction. And so very simply, an example, the square root of 3/4. I can split it and make it the square root of 3 over the square root of 4. And since I know the square root of 4, I can go ahead and turn that into 2. And that one's simplified. We can do that with letters, with numbers, but basically you can always split a radical across the fraction. All right, so what's the second thing? The second thing is we're not allowed to have any radicals in the denominator of a fraction. So this is a little bit different. The last one we had fractions on the inside. Here we're going to have a fraction, but it just has a radical in the denominator. So you can see here I have 1 over the square root of 2. What we're going to do is we're going to multiply. And we need to talk a little bit about this, and we'll kind of do that through a couple of examples we're going to do here. We're going to multiply to clear it out. It's always important, since we're working with fractions, you have to multiply the top and the bottom by the same thing. Otherwise, you actually change the fraction, and that's bad. So here's what we have. I have 1 over the square root of 2. Well, we know that the square root of 2 squared is 2. Okay, remember we said if the index and the power match, you just get the thing on the inside. We said that in a previous section, and I'm going to say it again. If the index, in this case 2, right, for the square root, and the power match, you're just left with that number on the inside. So I have a square root of 2, which means I just need another 1 to make that square, right? There's 1, there's another, that's 2 of them. That's a square. So if I multiply the top and the bottom of this fraction by the square root of 2, on the bottom we get just 2 because root 2 times root 2 is 2. And on the top, 1 times the square root of 2 is still just the square root of 2. All right, but what if we have bigger indices? Okay, with square roots it's pretty easy. You just make the two things match, you multiply, and it goes away. What if we have something bigger? Like in this case, 5 over the third root of x. Okay, so now we have to remember again, and I wrote it down here, or I wrote something about it down here, that in order to get rid of the radical, again, the power on the inside and the index have to match. So you can see down here at the very bottom, I have the third root of x cubed, and that's just x. And again, if the index and the power match, that will always be true. So we have to ask ourselves, well, what do we have, and what are we going to need to get us to those matching index and power? Well, in this case, I have x to the first power, and so if I need x cubed, that means I need 2 more, right? Because 1 and 2 more makes 3. So since I need to end up with 3, and I've already got 1, I have to use 2 more. So I use the third root of x squared. Because again, if I multiply those together, we're allowed to put those radicals together. That's another one of our properties. We put those together because they have the same index. And so x times x squared is x cubed. We get our x, and so we're pretty happy. We multiply the top and the bottom of the fraction by that same thing, the third root of x squared. And we end up with 5 third roots of x squared all over just plain x. Right? Because 1 here and 2 there makes 3. So the radical disappears, leaving the x. So there's a couple of examples. I'm going to do another example, kind of like the second one here, as soon as I get the next board up, and then we'll look at the third thing that we need to have if we're going to simplify radicals. All right, so like I said, I have one more example for cleaning up the denominator. So another way you might see the directions for this, and I probably should have written on the board, but I didn't. When you have a radical in the denominator and you're trying to get rid of it, we will call that rationalizing the denominator. And so let's actually write that down. Rationalize the denominator. And so all that means is get the radical out of the denominator. All right. So let's look at this example because it's a little bit different from what we saw on the last board. I have 7 over the third root of 4. And so maybe at first glance you're like, hey, that looks exactly like what we had on the last board. We have the third root of something. We need 2 of them, right? I need 2 more 4s because I've got 1 4 and I need 3 to get rid of it. But here's the thing. 4 is the same as 2 squared. So we can actually do a better job here if we recognize that 4 is 2 to the second power. Because once we recognize that, we can rewrite the problem as 7 over the third root of 2 squared. And now we don't need 2 more. We just need 1 more 2. Right? I've got 2. I need a total of 3 to make that radical go away. So I can multiply by the third root of just plain 2. So when I do that, again, those 2 things are going to make the radical go away and leave us with a 2. But we do also multiply the top by that same thing. So we get 7 third roots of 2 all over 2. And there we go. That's basically rationalizing the denominator. All right. The last thing we have to be able to do in this section. Okay, and then with any luck, I'll do a couple of more examples after this one. None of the factors inside can be written as powers greater than or equal to the index. Okay. So here's what we're looking at. I've got an example. I'm going to try and use that to explain it. I have the 4th root of x to the 7th power. All this one means is that power right there cannot be greater than or equal to 4. If it's bigger than or equal to 4, we're going to have to simplify it. Okay, because in this case, 4 is that index. So there's a shortcut, and I'm going to write that out on the next board for you, but I kind of want to show you where this is coming out of. So the idea here is kind of straightforward. I have x to the 7th, and from what I know about exponents, I could write that as x to the 4th times x to the 3rd. Now, why did I choose to write it that way? Because you'll notice that this first x here now has a 4th power, which matches the index. Okay, and that's going to be really important. So I can rewrite the x to the 7th as x to the 4th times x cubed. What that allows me to do then is, because I have multiplication, I can split up that radical. Okay, we can split radicals across multiplication and division. Never across addition and subtraction, so don't do that. So anyway, I can split it, which gives me the 4th root of x to the 4th times the 4th root of x cubed. Well, what is the 4th root of x to the 4th? It's just x, right? Because the index and the power match. And we've been saying here throughout this section that anytime those 2 things are the same, you just get that letter that was on the inside. So this whole first piece turns into just plain x. So I have x times, and you don't need the dot, I'm just putting it there to try and help things out a little bit, help us see it a little more clearly. X times the 4th root of x to the 3rd power. So here's kind of where that's going to get us, and like I said, I'm going to write this down on the next board for us. We're actually going to take any exponents we have and divide by the index. When we do that division, 4 goes into 7 one time. The 1 is how many x's will come out, and there's that one, the out. And if you finish up the teeny little division problem, 1 times 4 is 4, subtracting you get 3. Notice that the 3 then matches the x's that are left on the inside. So we can always take the exponent and divide it by the index. The quotient, the number at the top, that's the answer to that division problem, is how many come out. And so if this were a 2, I would have x squared there. And the number at the bottom is how many stay in. And that will work every single time as long as you have multiplication. So I'm going to put that on the board, on the next board, and then we'll do a couple of examples. So here we go. All right, so here I wrote out the directions for pulling those factors out of the radical. First, we're going to factor any numbers we have in there into their prime factors. That's kind of an optional step. There are other ways to do it, but it is a way that works really, really well. And so I'll look at that here with the second example I have on this board. 2, divide all exponents by the index. When you do that, step 3, the quotient is how many are going to come out. The remainder is how many will stay inside. So let's look at a couple of examples. First, I have the third root of x to the fourth, y to the eighth, z to the ninth. That's a mess. It's going to be a mess when we're done too, but it'll be a little bit nicer mess. So I divide. I start with the x's. 3 goes into 4 one time, so I pull out 1x. And the remainder is also 1, right? 3 goes into 4 once with 1 left over. So quotient and remainder goes in once, leaves 1 behind. For the y's, 3 goes into 8 2 times. So there's my y squared on the outside. And the remainder, if you do that division, is also 2. So we get a y squared on the inside. The last part, the z's, 3 goes into 9 3 times, so I pull out z cubed. But notice that this time, I don't have any remainder, right? The remainder is 0. So notice I didn't put any z's on the inside. All those z's came out. And there we go. That's done. So really, doing this with variables is really straightforward. You just go right down the line and you divide all those exponents. The quotient, the number of times it goes in, goes on the outside. And the remainder, how many are left over when you do that division, goes on the outside. All right, but what about numbers? And then I'll do one more bigger example on the next board because I'm out of room here. Well, so what about like the 4 through to 64? So there are ways you can do this that don't involve making factor trees. If you were able to recognize that 64 is 4 times 16 and that the 4 through to 16 is 2, then you'd be all set. You could do it that way. Sometimes that's really hard to see though. Unless you spend way too much time with numbers, like say me, you probably don't look for things like that just naturally. I'm a nerd. I'm weird. I see that, but I do this all the time. That's what I do. So anyway, since that's probably not you, we can make factor trees. Remember, hopefully you've done factor trees before. The important point here is that when you split it, the two numbers below have to multiply to be the number above. So in this case, 4 times 16 is 64. There were other options you could have chosen, 2 and 32, 8 and 8 would have probably been a good one. It really doesn't matter as long as they actually multiply. 4 then splits up into 2 times 2. 16 does a lot more work, splitting up into 2 and 8, which then splits into 2 and 4. And anyway, we have lots of 2's. Grand total, when we're all done, we have, I like to circle down, 1, 2, 3, 4, 5, 6 2's. Remember, I don't need anything that got split up. So even though there's a 4 and a 16 on this, I don't need those because they got split up further. So I'm just using the 2's. I have 6 of them. So my 4th root of 64 turns into the 4th root of 2 to the 6th power. Well, once I get it here, I can do the same thing that I did up above with the letters. 4 goes into 6 once, so I pulled out 1, 2. 4 goes into 6 once with 2 left over, so I left 2 2's on the inside. And then just because I don't like that, the way it's written, I'm going to do the 2 squared and turn it back into a 4. So there we go. All right, and I'm going to do one more example real fast on the next board. All right, last example before I make a video that's too long and YouTube doesn't let me upload it. All right, the third root of 81, x squared, y to the 4th, z to the 5th, a to the 8th. So I started by factoring the 81. I made I just knew what it was because, again, I do this too much. You feel free to make a factor tree out of that 81. You will get 3 to the 4th. So then I divided. 3 goes into 4 once with 1 left behind. So 1 3 out, 1 3 in. For the x's, 3 doesn't go into 2. So you'll notice I don't have any x's on the outside. And so both of them stayed on the inside. 3 goes into 4 for the y's, 1 time with 1 left over. 1 out, 1 in. 3 goes into 5 once for the z's, so I get 1 z on the outside with 2 left over on the inside. And finally, 3 goes into 8 twice, so I get a squared on the outside. But it has 2 left over, so it also gets an a squared on the inside. And that's basically simplifying these things. So, good luck.